Okay, so let us continue our discussion on the transformer protection. So, we have discussed that earlier that we can use the circulating current differential protection, and in that circulating current differential protection two problems are there. The first problem, that is the problem of the spill current, and this spill current that flows through the relay because of the non-identical CT saturation characteristic, and the second, that is the unequal lead length, right. Because of this two problems, the differential current that flows through the relay and relay may maloperate if we go for circulating current differential protection scheme. So, the remedy is to use the bias or percentage differential protection scheme. So, in earlier case circulating current differential protection scheme, the relay, this is the relay, right, it has only one coil, that is known as the operating coil, through which the I1 minus I2 or the differential current flows. Now, in bias or percentage differential protection scheme, the another coil, that is known as the restraining coil, is also connected. So, the operating coil is connected at midpoint of restraining coil. So, the current here, that is I2, and this current, that is I1. So, the current through this operating coil is still remain I1 minus I2, right, if I take absolute value, and if the restraining coil has n number of turns, then the current flows for half of the turns, that is the I1, and the other current that flows through half of the turns of the restraining coil, that is I2. So, the again the value will be I1 plus I2 by 2. So, the current that flows through the restraining coil, that is the average restraining current, is the average current, that is the I1 plus I2 by 2. So, if we use this, then because of these two problems, non-identical CT saturation characteristic and the unequal lead lengths, I2 and I1, even though they are not unequal, and still spill current flows, then also this relay has two settings. The first setting, that is known as the basic setting or the sensitivity setting. So, this basic setting or sensitivity setting, that is given by I1 minus I2. So, this is the current that flows through the operating coil of the relay, right, that is the bias differential relay. So, this is the first setting, that is known as the basic setting or the sensitivity setting, right. The second type of setting, that is known as the bias setting. Sometimes this is also known as the percentage bias, or sometimes it is also known as the slope setting. So, the slope setting is given by the ratio of I1 minus I2 divided by I1 plus I2 by 2 into 100. So, this you will get in percentage. So, you can see that if in the case of circulating current differential protection, spill current I1 minus I2 flows because of two problems as we have discussed. In case of bias differential relay, even though differential current is there, spill current is there, and this setting exceeds, but the percentage bias setting, that is not going to exceed, because even though I1 minus I2, that is spill current flows, this the denominator you have the average restraining current, this also increases. So, the percentage bias reduces. So, that means if I consider the bias setting, then using this setting, whatever is the problems faced by the circulating current differential relay because of the non-identical CT saturation characteristic and the unequal lead lengths, or because of the flow of spill current, this type of problem that can be avoided if I use biased or percentage differential protection scheme. Now, let us discuss what is the characteristic of biased differential relay. So, the characteristic of this relay, that is given or plotted, considering on y axis we can consider the differential current, that is I1 minus I2, and on x axis I will consider the bias current, that is I1 plus I2 by 2. And you can see that the characteristic is like this. So, any portion above this characteristic, that is the operating region, and the portion below this, that is the blocking region. Now, when we consider the any point, right, say the differential current flows or the spill current flows through the relay because of two reasons, then that point, because of increase in this value restraining current, that will again come or fall down somewhere here. So, it is always in the blocking region or non operating region. So, relay does not operate and the mal-operation of the relay that can be avoided. Before we apply this bias differential relay or any type of differential protection scheme to the transformer, power transformer, right, we are talking about the power transformer, then a few points we need to consider. Let us see what are those points. The first point, that is the line charging transformer primary rating. Now, we know that the transformer voltage and current rating, that is entirely different. So, if I consider LV side and HV side, the currents are entirely different. So, whatever CT we use, then in that case the CT ratio is also different. Why CT ratios are different? Because suppose for example, if I consider 220 kV by 132 kV delta star transformer, the MVA rating is 100, then the current on 220 kV side and 132 kV side are different. So, whatever CT ratio I have to consider or select on 220 kV side and 132 kV side, both are also entirely different. For example, for 220 kV side, we have to consider the CT ratio, that is 300 by 1 ampere for the CT located on 220 kV side, and for the CT located on 132 kV side, the CT ratio I have to consider, that is 450 by 1 ampere. So, you can see the primary rating of both this CT1 and CT2 on each side of the transformer, that is entirely different. However, the secondary rating, that is always same, it is always 1 ampere or 5 ampere. If the current is above 1000 ampere primary side, then the secondary rating, that is 5 ampere. If the primary current is less than 1000 ampere, then it is always 1 ampere. So, that means the primary ratio is, let us say, below 1000 by 1 ampere, then you always go for CT secondary, that is of 1 ampere, and if it is more than 1000 by 1 ampere ratio, then you will go for the 5 ampere CT secondary. So, this is very important and this point need to be considered when you consider the or when you apply the differential protection scheme in case of the power transformer. Why this is important? Because this primary rating, that is different, even though secondaries are different, these two secondary currents are different, and when you apply these two currents to the relay, differential current that always flows through the relay. So, this need to be take care when you apply the differential protection in case of power transformer. The second point we need to consider is the no load current of the transformer. We know that the primary current of the transformer, that is given by the IP primary current, that is equal to IS times some transformation ratio, K is the transformation ratio, and the IS is the CT secondary current plus I naught. So, I naught is the no load current of the transformer that contains magnetizing component as well as the some loss component. The no load current of the transformer, that is roughly 1 to 2% of the full load current of the transformer. And when you decide the setting of the relay, then that relay is capable to take care of this point, that is no load current of the transformer. Let us discuss the third point we need to consider when we apply the differential protection scheme for the power transformer. So, this third point, that is known as the inherent phase shift, exists in the power transformer. Now, when we consider the delta star transformer, and we know that in actual substation practical field, whatever transformer we use, power transformer, that is either of dy1 vector group or it is either of dy11 vector group. The other vector groups dy7, dy5 are not used. So, we use only out of either dy1 or dy11. So, here I have shown the diagram for the dy1 vector group. So, this is for dy1 vector group, delta star transformer with the connection 1. Now, when we consider this, you can see that this current capital IR and small IR, these two currents are equal. Why? Because when you mount the transformer, these two coils are again mounted on the same limb. So, this capital IR and small IR both are same. So, if I draw the vector diagram, then you can see this small IR, I1 and IB both are all are 120 degree apart, and this IR, that is in phase with capital IR, capital IY that is in phase with this is in phase with this IR, and this IB that is in phase with the small IB, right. So, this is very important. However, if I just look at the current, this current IRL, then this IRL is nothing but from this point if you measure, that is IR minus the current available from B phase, that is IB. So, this IRL that is nothing but the IR minus IB. So, if I draw a vector diagram for IRL, then it is IR minus IB. So, your plus IB is here. So, if I extend this, then your minus IB that is here, and if you add this to IR and minus IB, then you will get the value of IRL that is here. So, if I compare this IRL and the small IR here, these 2 points, then you can see that capital IRL and small IR, there is a phase shift exists between these two. If I consider this diagram considering the primary or the IRL as a reference value, then the secondary current IR always leads the primary current IRL by 30 degree, right. This is the 30 degree. So, that is why, or sometimes it is also known as 1 o'clock, right. So, this type of connection is known as 1 o'clock connection, that is why the name given dy1, right. If I consider the dy11 type of vector group, then the phase shift available, that is the minus 30 degree, and the available point that is somewhere like this, like 11 o'clock, that is why the connection name given, that is 11. And in this case, the secondary current IR lags the primary current IRL by 30 degree, that is why the minus 30 degree connection or 11 o'clock connection. So, whenever we give or whenever we apply differential protection scheme, bias differential relay to the transformer, delta star transformer, then as we have discussed that there is an inherent phase shift of 30 degree plus minus depending upon the vector group we use, either 1 or 11. Whenever we apply the differential current or CT secondary current from LV side and CT secondary current from HV side to the relay, the differential current always flows through the operating coil. So, this current, these 2 currents given to the relay, that is equal in magnitude as well as in phase. So, this is very important. Differential current should be same in magnitude as well as in phase. So, we need to do some arrangement to compensate this phase shift, inherent phase shift that exists in the delta star transformer depending upon the vector group used, either dy1 or dy11. So, how to avoid this? So, to avoid this, what we do is, this is your delta connected delta and this is star, right. This is again the dy delta star 1 connection. Now, so the remedy to compensate the 30 degree phase shift, whatever delta side of the winding connection is there, whatever CT I use here, that CT I connect in star, and the star side, star winding of the transformer, whatever CT I use, that I connect in delta. So, delta side, the whatever CTs I used, line CTs are connected in star, and on the star side the line CTs are connected in delta. Keep in mind this delta should be same as your dy1 like this, right. So, if you connect like this, then the whatever phase shift is there, that can be avoided, and whatever current, you can see that the primary current is IRL, IYL and IBL on delta side. So, the secondary current 180 degree out of phase, that is IRL and IBL. This current should be equal to the current given on this side, that is IR, IY, IB. So, small IR, IY and IB, these 2 currents, this current and this current should be same, this current and this current should be same, and the other, this current and this current should be same. So, these 3 currents are equal in magnitude as well as in phase, because this is the relay which has a bias differential relay which has 3 operating coils and 3 restraining coil, 1 for each phase. So, that means if we go for any compensation, then we have to connect the line CTs like this. Moreover, if we connect like this, then this is also going to eliminate the 0 sequence current on the star side, while the 0 sequence component on delta side, that is not produced outside the delta, it remains circulated inside the delta. On the other hand, if I use the star star connection, then the CTs on both the sides that should be connected in delta, but however star star connected vector group normally we are not using, we use either dy 1 or dy 11. The next point, that is, or the next factor we need to consider, that is the bias to cover the tap changing facility. We know that most of the power transformers are inherently contain the tap changing facility. So, tap changing transformers are widely used, and hence the CTs that can be chosen based on which tap, highest tap, nominal tap or the lowest tap. So, normally when we decide the CT ratio, we decide the CT ratio based on the nominal tap or the fixed tap. This is normally the central tap, right. So, the transformers operation that for any tap other than the nominal tap or the central tap, if that means if we decide the CT ratio based on the nominal tap, and then if I change the tap and put the or use the highest tap, then in that case because of the mismatch some current that will always flow through the relay. So, this current need to be compensated, and this is known as again the spill current. So, the mismatch of the current that will be over and above the mismatch because of the non-standard CT ratio or unequal lead length. So, the unbalanced current that may be sufficient to cause the relay operation. So, in practice there are two options. How to what is the remedy of this? The remedy is we can go for either bias differential relay, right, and bias differential relay, even though we use bias differential relay, then this relay settings are decided based on the nominal tap. So, we have to consider the worst case and then we decide the setting, particularly the bias setting of the differential relay. But however, we decide the setting based on worst case, then for other conditions the sensitivity or the operation of the relay that is affected, right, it reduces the sensitivity. So, the best option is we need to go for the adaptive setting. So, we know that ideally the differential current should be 0, however, it is not 0 because of the reasons as I have explained you, right, because of the tapping. So, this situation is more serious. Now, if we consider the difference in the mismatch that is lower than the bias, whatever percentage bias setting or slope setting, that can be easily take care of this. But if the difference in the current because of tap change in tap, either highest tap or lowest tap, this difference is high, very high, then the bias is not capable to take care of this. So, in that case we need to change the bias, percentage bias adaptively based on the change in the tappings of the transformer. So, this is known as the adaptive setting. So, sometimes it may possible that whenever we use delta star transformer, then on, as I told you, delta side we have to connect the line cities in star, and the star side we have to connect the line cities in delta, so that the 30° phase shift can be easily compensated. However, sometimes in actual field they do not connect the both side means star delta side star city and star side delta city, they connect both sides star star. So, in that case you have to use the other option that is known as the interposing current transformer. So, interposing current transformers are again the non-standard CTs, and this CTs are at low voltage. That means, if I wish to compensate the magnitude of current as well as phase shift at lower voltage, lower current, then we can go for the interposing current transformers. So, in this case when we use the interposing current transformers, it can be easily compensate the whatever is the mismatch in the magnitude and the as well as in the phase. So, this type of CTs are always connected on the secondary side of original or actual current transformer. So, on the secondary of CT you connect one more transformer that is known as the ICT, and that is going to compensate the magnitude as well as the phase of the differential relay, so that the current fed to the in each phase of the differential relay that is equal in magnitude as well as in phase. Now, the next phenomena that is known as the magnetizing inrush current. So, magnetizing inrush current is a condition when the transformer draws a very large magnitude of current, while the load current is either 0 or the nominal magnitude. That means, when you energize the unloaded or lightly loaded power transformer, then the transformer draws a very high magnitude of current and that current is known as inrush current. Keep in mind this inrush current is not a fault. However, whenever it draws a current inrush current, its magnitude is maybe 5 to 10 times the full load current of the transformer. So, whatever relay we connect, it treats such type of phenomena as a fault, but actually it is not a fault, because it is going to die down once the normal condition is established in the transformer. Now, to understand this phenomena, let us consider the voltage waveform between the voltage and flux with reference to time and the phase difference between these two, that is theta, let us assume. Now, when the flux that is going to established inside the core of the transformer, when you energize the unloaded or lightly loaded transformer, then this flux can be asymmetrical or symmetrical in nature. So, whether the flux that is going to establish in the core of the power transformer, that is symmetrical or asymmetrical in nature, that depends on the switching instant of the voltage signal. That means, whatever this voltage signal I have shown, at what instant you are energizing the transformer, that is going to decide whether the flux that is going to establish in the core of the power transformer is symmetrical or asymmetrical. If the switching of the transformer is carried out when the voltage wave is passing through its peak value, right, like this here its peak value, then the flux that is going to establish in the core of the transformer, that is symmetrical in nature and it is given by phi, that is phi max plus or minus phi r, where phi max is the maximum value of steady state flux that is going to establish in the core of the transformer, and phi r, that is nothing but the residual flux in the core of the transformer. Now, in this situation what will happen, as the flux is symmetrical in nature, so BH curve or whatever point that always operates in the linear region of the BH curve, and hence the magnitude of inrush current that is restricted to a small value. To understand this, if I consider that this is the voltage waveform and according to this they establish flux that is symmetrical in nature, right, you can see there is a symmetry in positive and negative halfway. So, if I extend this point blue dotted line, then you can see on hysteresis curve these points are always in the linear region of the BH curve. So, if I further extend downward this blue point, then you can see that the inrush current, magnitude of current, that is normal, that is not very high, right, and you can see that whenever the flux that is which is going to establish in the core of the transformer, that is directly proportional to the current, right. So, magnetizing inrush results in a large flux value or flux density in the core of the transformer. At this point of time, the core volume of the transformer that remains minimal. So, whenever transformers are designed to operate, they have to design such a way that it always operate below the knee point. So, if point exceeds that value, transformer enters the saturation region and it is not in the linear region of the BH curve, but it is in the non-linear region of the BH curve. Now, conversely, if the switching of the transformer is done when the supply voltage is passing through its 0 value, then the whatever flux that is going to establish, that is asymmetrical in nature and that is given by again the same equation, but the 2 that comes in picture. So, in this case the upper point of the BH curve that gets elongated, it does not remain in the linear region of the BH curve, and hence in order to produce the same amount of flux, the magnitude of currents that becomes very high. So, you can see that the here I have shown the asymmetrical flux, right, and because of this point that is comes somewhere here, and if you it is not in the linear region of the BH curve. So, if you extend these 2 points green point, then the magnitude of current to produce the same value of flux that is very high, and this current is known as the inrush current. The magnitude of this current is almost 10 to 12 times the full load current of the transformer, and because of this inrush current, this is going to damage the transformer. Because of this, there are fair chances of maloperation of the differential relay, because differential relay treats this phenomena as a fault. It is also going to keep adverse effect on the power quality, and it also produces the DC component. This is because the flux produced is asymmetrical in nature. So, this asymmetrical flux contains the decaying DC component. So, the nature and magnitude of inrush current how much value it attains, that depends on the direction and the magnitude of the residual magnetization flux in the core and the switching instant. That means, at what instant of voltage you are energizing the transformer. Now, how to avoid this, how to detect this, because inrush is not a fault. So, if I go for harmonic analysis of the flux wave shape, then it is found that the DC component with reference to the percentage of fundamental component, that is 55 times, the second harmonic is 63 times, and third harmonic, that is almost 26.8 times. The other harmonics goes on reducing with reference to the percentage of fundamental component. So, if I detect this two component, right, or the DC component, then I can easily identify the inrush pattern or inrush point, and hence we can block the operation of the relay. So, in normal practice, what they are doing is they normally monitor the second and third second harmonic component. So, if second harmonic component exceeds say 20%, then the operation of the relay is blocked, indicating that it is an inrush phenomena, it is not a fault. So, different techniques are available. These techniques are harmonic restraint technique, harmonic blocking technique, DC biasing technique, as the DC component is also significant, and sometimes wave shape monitoring technique is also available. Now, let us consider one example. So, in this example you need to draw a protection scheme for a power transformer that contains bias differential relay. You need to suggest a suitable CT ratio on both sides of the transformer, along with you need to suggest the ratio of interposing current transformer, that is ICT also. Furthermore, to provide the proper verification, you need to also say that whether the bias differential relay will operate in normal condition or pre-fault condition or not. The data are, the power transformer rating is given 250 MVA, 15.75 by 440 kV, it is DY11 type transformer. It is a tap changing transformer, so tappings are provided from -% to +7.5% on HV side. The reactance is the 14.59%, and you need to assume this ratio error of the all CTs, that is plus or minus 3%, that means normal CT as well as the interposing current transformer, that is ICT also. The bias differential relay that is connected, it has two settings. One is the sensitivity setting, that is 15% of 5 ampere. It has three variable settings 10, 20 and 30, and the second setting, that is the bias setting, also provided. It has also the high set instantaneous setting, which is 10 times the rated current or full load current of the transformer. The relay is equipped with second harmonic restraint feature, that is if it exceeds 15%, the operation of relay is blocked, and the relay has also a feature of fifth harmonic bypass, which avoids unwanted operation of transformer in case of over excited condition. So, over excited condition is a special type of phenomena that occurs in the transformer when the voltage is high, above nominal value, and the value of flux, that is below the nominal value. So, the V by F flux, this ratio increases, and this is not a fault, but it is just over excited condition, and relay has to discriminate between fault and over excited condition also. So, in this case, let us first find out the full load current of the transformer on primary side. So, the rating 250 into 10 raised to 6 by root 3 into 15.75 kV. So, current comes out to be 9164 ampere. So, I select 10,000 ampere by 5 ampere. I have selected 5 ampere CT secondary because this current is more than 1000 ampere. If I use this CT ratio and if I transfer this current on secondary side, then the current comes out to be the 4.582 ampere. So, 9164.28 multiply by 5 divided by 10,000. So, your current comes out to be 4.582. Similarly, if I find out rated current on secondary side, then that is 250 into 10 raised to 6 divided by 440 kV. So, the current is 328 ampere. I can select 500 ampere by 1 ampere CT. I have selected 1 ampere secondary because this current is less than 1000 ampere. Here you can go for 350 ampere also, 400 ampere also, 450 ampere also, because CTs, standard CTs are available in the multiple of 50s, but I have selected deliberately 500 ampere looking into the future load growth. If I transfer this current on secondary side using this CT ratio, then the current is 0.6561 ampere. So 328.04 multiplied by 1 divided by 500. So it comes out to be this current. Keep in mind this current and this current are not equal, right, because these two currents are not equal. You have to give this current to the differential relay, and whenever you give magnitude as well as phase wise, these two currents are equal. So that is why we have to introduce the interposing current transformer. So this is the schematic diagram you have to draw. This is your delta star transformer with the DY11 feature. This is delta connect winding, this is star winding. On delta side I have connected 3 line CTs in star, and on star side also I have connected in star. Even though we have discussed earlier that delta should be this should be connected in star, this CTs should be connected in delta, but I have not used because I have used the interposing current transformer. So you can see that on the delta side these 3 currents are known, that is 4 point, you can see how much, 4.582 ampere, and this currents you have calculated, that is 0.6561 ampere. So this currents, that is 0.6561 ampere. So these two currents are not equal. So by some means we have to do some arrangement so that these two currents are equal, and for that we have utilized the interposing current transformer with one side winding, that is star connected, right. So CT secondary of 500 by 5 ampere, that is directly connected to this. So this currents, that is same. On the other side, the other winding of the ICT, that is delta connected. So this delta connection is similar to this delta connection, you can see, and the currents, this current through this winding is IR1, IY1, IB1, and the current available, that is IR2, IY2 and IB2. So let us find out these two currents. Now see, this currents is 4.582 ampere. So obviously this currents, that these 3 currents are also same as 4.582 ampere, right, because we need to decide ratio of ICT, which is not given. So this currents, that is also 4.582, then and then the current given to the bias differential relay, that is equal. So if I find out the current, if this currents are 4.582 ampere, then obviously this current we can easily find out. So this IR1, IY1, IB1, that is nothing but the 4.582 divided by root 3. So this comes out to be 2.645 ampere. So the ratio of ICT should be 0.6561 divided by 2.645, or if I convert it, then it should be 1:4.1. So if I consider this CT ratio, that is 1:4.1, and if I consider the highest tapping, that is plus 7.5%, then with this let us find out what is the ratio. So the normal ratio is 440 kV by 15.75 kV. If I multiply this, if I consider 440 kV by 15.75 kV as the one value, then at tap plus 7.5%, the value comes out to be 1.075. So if I multiply this with 1.075, then the ratio comes out to be 473 kV by 15.75 kV. So on the secondary side of the transformer, the reactance value is given. So what is the fault current on the secondary side of the transformer? This current we have already calculated, full load current on secondary side of the transformer, divide by this. So the fault current on secondary side, that is 2248 ampere. If I use this, that is 473 kV by 15.75 kV, and if I find out the fault current on primary side by multiplying this current with this 473 kV by 15.75 kV, then the current comes out to be this value. If I transfer this current IPF 67 kilo ampere and ISF, that is 2248 ampere, if I transfer these two currents on secondary side using CT ratio 10,000 by 5 and 500 by 1, then the current comes out to be these two values. Now we have to consider ratio error in the CT. So if I consider the worst case, primary side plus 3% ratio error, secondary side minus 3% ratio error. So if I consider plus 3% here, minus 3% here, the current comes out to be like this value. So further, now we have to consider this current, that is the ISF. These currents are available somewhere here, right. So, when I consider this IFF, then if I multiply with the ratio of ICT, which is 4.1, then the value of current comes out to be this value. If I further consider minus 3% error in this, then the value comes out to be this value. And if I this value is where? This value is somewhere here, right. And if I multiply this value to find out the ISF2, then I have to multiply this value with root 3. So, it value comes out to be 13.05 ampere. So, in previous case the value is 34 ampere primary side CT secondary, and on this side the value is this. So, if I take the difference of these two current, then 34.192 minus 30.02. So, differential current is 4.142 ampere, and the percentage bias, if I use this value, then it comes out to be 8.42%. Now, see the setting which is already given inside in the data. If you refer the data, then the setting that is given is the bias differential relay has a fixed setting, that is 15% of 5 ampere. So, if I take 15% of 5 ampere, then you will get value, and the other setting that is given 10, 20 and 30%. So, with this you can see that I can select this bias setting as 10%, but considering the CT saturation and mismatch, I can go for the higher setting, that is 20%, right. So, this we can consider 20%, and this value you can see that it is 15% of 5 ampere if you take, then this value is also comparable. So, this is all about the how we can calculate how we can apply the differential protection in the transformer, and how we can calculate the CT ratio, ICT ratio, and how we can equalize the current fed to the differential relay in magnitude as well as phase wise. So, in this session we have discussed the different factors to be considered while we will apply the differential protection scheme to the transformer. We started with the tappings, we also consider the magnetizing inrush phenomena and some other factors also, and then we have solved the example. Thank you.